everyone. In this video we're going to start section 1.6, in which we tackle the first part of the fundamental theorem of calculus. And in some ways we're going to be a little bit, willy-nilly with this. I'm not going to actually prove anything to you. I'm just going to offer what I think is a fairly good argument for what I'm about to say. When we get to the second part in 1.8, the second part of the fundamental theorem, we'll have a lot better justification for why we're doing what we're doing here. But the second part of the fundamental theorem is a little more confusing to people. So they're very closely linked. They're saying a lot of the same things. The fundamental theorem is extremely important. We're going to start with the part that tends to be a little bit easier for people, even though that means we have to start with not a perfect justification for why it works. Okay, so here's our good argument for why the first part of the first fundamental theorem works. So we want to consider a velocity problem. And I'm giving you an equation and I'm giving you a graph. And we have now talked about two different ways that we could find the total distance traveled, the change in position from t equals 1 to t equals 5. So one way to do that would be to say, okay, if I have a velocity function, whoa, I don't want the crazy red. I want blue. Okay, so if we have a velocity function, don't mind me while I'm really slow about writing this. Okay. 1.6. We can get a position function by finding an antiderivative. So the antiderivative of this thing is going to be what we go up to 4. So we have 0.1 over 4 t to the 4th. So bump the power up by 1, divide by the new power. Here we have 1.2. We're going to have to divide by the new power, which is 3. And then that'll be times t cubed. And then we have a 4.8 that'll have to be divided by 2, t squared, and a 1.6t. And then we'd have some initial position plus c, or we can even call it plus s sub 0. And velocity function. We don't need to know what s sub 0 is. We don't have enough details here, I don't think, to just say that it's 0. But it's not going to hurt us to have it in there. Oh, yawning. Okay. So s of t is, well, I don't even know if I care to simplify. So I'm just going to kind of walk through the process. So we find an equation, s of t, which is the antiderivative. We would then say, okay, well, I need to know what was our time, t equals 1 to t equals 5, how far I've gone after 5 seconds, and I need to know how far I've gone after 1 second, and to find the displacement, the change in position, I'm just going to subtract. So this is how I would do it. Again, I'm not going to bother crunching through perfectly on this because that's not really my point, but hopefully that makes sense. Okay, the other thing that we have been working on lately is the fact that we could use this as an area question. If we have a velocity function, the area under the velocity function should equal our displacement. So if we're going from t equals 1 to t equals 5, this area should equal our displacement. Change in distance. And we even have new notation for that. The change in distance should then be equal to the integral of this velocity function from t equals 1 to t equals 5. Okay, so what the first part of the fundamental theorem of calculus is going to claim, and it's actually going to be a little bit more general than this, but we'll use this as our starting point, is that we sure as heck better hope then that when we integrate the velocity function from t equals 1 to t equals 5, that we get s of 5 minus s of 1. So we're going to say this is our claim, and I'm not really going to prove it to you for a little while, but that's what we should be noticing. We've got two ways to do this. They sure better give us the same answer if things aren't being really weird. So a little bit more general claim would be that this holds true even if it's not a velocity function. So we're going to call this Fundamental Theorem of Calculus Part 1. And what we're going to say is that if big F prime is equal to little f, then the integral from a to b of little f of t dt should equal big F of b minus big F of a. And hopefully you can see that that's the same claim that we made before, just in a little bit more general situation. So if the derivative of big F is little f, that means big F is an antiderivative of little f. So if we want to figure out the value of the definite integral of little f, we would need to find out what the antiderivative is and then plug in our limits of integration. The upper limit plugged in, so let me think how I want to say this. The antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit gives you the area under little f. In the context of word problems, this will get called the net change theorem. I don't care if you remember that it's called that. And that would just be saying that if you are integrating a rate of change function, so if little f of t gives rate of change in anything, let's say it's the rate at which rain is falling. So the rate of change in the amount of rain that's fallen. Then big F of b minus big F of a gives the net change. So if we're talking about the rainfall, if we integrate the rate of rainfall from, say, 0 to 3 hours, say we're talking about hours, that should give us the net change in rainfall. So the total change in rainfall over those 3 hours. We'll do a ton of these later, but just to mention it now. I'm trying to think if there's anything else I want to say here. There can be some other restrictions. We want some continuity and things, but just to get you started, this is what we're looking at for the Fundamental Theorem of Calculus Part 1. So again, what this does for us, and this is really powerful, and the second part is going to tie this all together again in a new way, is this says that to find the area under the curve, we're going to find an antiderivative, and then we're going to plug in the upper and lower limits of integration. All right, thanks for watching.